Our everyday reality seems to us clearly defined and unambiguous. Every object occupies its own specific place in space and moves at a certain speed. However, about 100 years ago, it became clear that this view was one of humanity's deepest misconceptions. Physicists realized that the world, where everything is definite and stable as we are used to seeing it in everyday life, cannot actually exist. On the most fundamental level, nature turns out not to be precise, but blurred and uncertain. But what does this fuzziness mean? And why is a world where everything is strictly determined physically impossible? We are used to thinking that everything moves along trajectories: cars, people, balls, planets. A trajectory is the symbol of a clearly defined world. If an object moves along one, its position and speed can be known exactly at every moment in time. Knowing an object's position, speed, and mass at a given instant allows us, using the laws of classical physics, to calculate its future path. Thus, if we measure the position and speed of the planet Mars, we can precisely predict its orbit around the Sun, even where it will be in 100 or even 100,000 years. On these principles rests our classical understanding of physics and everyday reality. More than a century ago, when scientists discovered that everything consists of atoms, they tried to apply the same principles to the microscopic world. An atom consists of a positively charged nucleus around which negatively charged electrons revolve. Since the electric attraction between the nucleus and the electrons resembles the gravitational attraction between the Sun and the planets, physicists assumed that electrons, like planets, move in orbits around the nucleus. They tried to calculate these orbits, but it was here that the theory broke down. It is known that any charged particle moving along a curved trajectory emits energy. Electrons are charged particles. Therefore, by circling the nucleus, they should continuously lose energy. Over time, the electron would be unable to resist the nucleus's attraction and would collapse into it. In that case, atoms would be unstable, and thus neither matter nor the world as we know it could exist. For a long time, physicists puzzled over this paradox. How can matter be stable if electrons should fall into the nucleus? The solution was proposed by a young scientist named Werner Heisenberg. He realized that to explain the stability of matter, one had to abandon familiar notions of nature. At just 24 years old, he published a theory of a new kind of physics that not only explained atomic stability, but also completely transformed humanity's understanding of the world. According to his ideas, a particle does not have an exact position. It is smeared out in space, existing in several places at once. This was a shocking revelation. The familiar categories of position and velocity, fundamental to classical physics and our way of thinking, are not actually the foundation of reality. Heisenberg showed that the concepts of position and velocity are merely convenient constructs that help us navigate the macroscopic world, but they do not reflect the laws of the microscopic one. Experiments confirmed that if we try to determine the exact position of an electron, its speed becomes uncertain. And if we measure its speed, the electron seems to dissolve into space, and its position becomes unknown. This rule became known as the Heisenberg uncertainty principle. Position and speed cannot be precisely determined simultaneously. There's always an inherent degree of uncertainty. And it's not due to imperfect instruments. This fuzziness is a fundamental property of the quantum world. As soon as we attempt to pin down a particle's trajectory, it seems to evade observation, refusing to obey the usual laws. For the electron, this means it does not orbit the nucleus like a planet around the Sun, but is instead distributed in space around it like a cloud. The probability of finding the electron in a particular region varies. It is higher in darker areas and lower in lighter ones. In this cloud-like state, the electron has neither a definite position nor a definite speed. And precisely because of this, the atom remains stable and matter endures. Today, nearly a century later, we know that the uncertainty principle applies to all objects in the universe. For large bodies, this uncertainty is negligibly small, so we don't notice it, and the world seems solid and definite to us. Yet, at a deeper level, the very fabric of the cosmos is permeated with this uncertainty, revealing that the true nature of reality is entirely different from what we perceive. Understanding Werner Heisenberg as a person is not easy. A genius who became a professor at 25, he was unafraid to question even the seemingly self-evident truths of physics. He claimed that the visible traces of electrons in a Wilson chamber were merely an illusion, not a representation of true reality. During World War II, Heisenberg took part in the German atomic program. It remains controversial whether he truly intended to build an atomic bomb or tried to obstruct the project. His life unfolded between brilliance and moral contradictions, at the crossroads of science, politics, and philosophy. Heisenberg's discoveries not only explained the stability of matter, but also forever changed our understanding of reality. The world we see is merely a simplified reflection of deeper processes governed by the laws of probability and uncertainty.